Okay, hello again. This is the third project, but the keypad project. I thought it's too simple, and you can do it as a self-study. So right now, I will explain how we are creating pulse width modulation with three different methods. Because this is very useful in different like applications. You will need for sure to know this, but the keypad is very simple. You just need to read that code that is in the 3.3, and in your final projects you can use any keypad. We have keypads in our lab, so if you need, I can give for your projects. Right now I have this connections for the motor that will be used. We have to run the motor using this power transistors, because the motor or a microcontroller cannot provide enough power for running the motor. So we are using separate power source. We have this on the table, the power source that we can get from the 5 volts. So we will use that as a power supply for the DC motor, and but we will control the transistor from our microcontroller. This is in reality how it happens. Microcontroller is just like the manager. It doesn't do the work itself. It just controls all of the other devices, relays, transistors, switches, so that they can do the job. Right now here we will have the pin D.5 connected to the base of the transistor TIP 122. You should have the 5 kilo ohms resistor here also, so that it limits the current. Plus side of the motor to the 5 volt and negative to the collector, and the emitter of transistor is connected to the ground. And important is that the grounds of both of this need to be connected here. Ground of the power supply, like table power supply that we have, and the ground of the or microcontroller board. And we have two push buttons that we will use, this S1 and S2, for increasing and decreasing the the power of the motor, the width of the pulse that we are using for controlling the speed of the motor. We can modify it with the two push buttons. S1 increase, for example, and S2 will decrease it. So this is how you will connect. LED is just for the test, it's extra. We can run the LED also with the pulse width modulation, but right now we will do this motor that is run by the PD5. So let's see how. First, we will use only the delay function. Let me see, what is the other picture? Here there is the other picture that we have. You can see there's only 4 pins that can be used to make pulse width modulation using the timers. These are using the timers, so we are not using the delay function. You can connect it to any of the pins, but if you want to use the timers for creating the pulse width modulation, you need to connect here, 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 or here, and they are controlled. This one is with the timer 0, OC0. You can see this one with the OC1, B, and A. This is controlled by the timer 1, and this one is OC2, output compare 2, which is controlled by the timer 2. So we have 4 pins that are pulse width modulation in Atmega 32. This we will use. Okay, let's go to the task, and I try to explain as fast as possible so it doesn't get boring. So we have 3 methods. First method is with just delay function. We disconnect power, connect power, disconnect, connect, disconnect, and with the delays that we make during the disconnect and connect, we create a pulse. This pulse, their difference is that if we use delay function, the CPU will be the only part that does all the computation. It's just all the time computing the delay, the everything, and if our program is big, basically we cannot add anything there. It just entire code will be used for counting the delays and connecting. So we cannot do much more over there. But we can, the other option is to use the timers, like timer 0 and timer 1 we will use in this one for creating the delay. Here the definitions, the descriptions are here, that the easiest if using the delay function, if we just need to turn an output on and off. It's explanation of how they are and what is their advantage, pros and cons. The short is that if you use delay function, 100% of the workload will be on the CPU. If you use like partly timer and partly CPU, CPU will be more free, a little work to do, or you can put 100% of the work on the timer and CPU would be totally free to do some other task. And let's go see what we are doing. I don't know. Right now in this code that you see here, all of the functionalities are configured so that all of the codes at the end, you can see 3 different codes. One, this code that is after the continue is just for using delay function. We use here just the delay. So if we didn't configure anything, like everything was as a default, we could just come here and write, just define an integer, and that is this. And yeah, for integer from 0 to 255, we could just tell if the DC is the duty cycle is defined. If I is smaller than duty cycle, port D should be on, else port D should be off. So this is like turning it. And the duty cycle would be some number between 0 and 255. And we will like modify the value of the duty cycle by with these loops. Here we say like the push, if duty cycle is bigger than the 0 and the push button PB0 is pressed, decrease the duty cycle value. And if the DC is smaller than 255 and the push button 1 is pressed, and the second push button PB1 is pressed, increase the value of the duty cycle. So with these 2 conditions, we will control the duty cycle. And these limits are because we don't want it to go to the minus, and it should not go over 255 also. So we want to have it in a range, and using 2 push buttons, it should go up and down. And here we say for I, like from 0 to 255, it's basically counting I1, and delay is 78 microseconds. So every I that is counting here comes here, makes a delay 78 microsecond, and then if I was, like for example, say here duty cycle is, we have decided to have a put DC duty cycle to be 50%. So 50% of 255 is 129 about. So if we had DC value to be 129, for half of this range, this I would be smaller than the DC. So this would be on. And for the other half of the range, when I was bigger than 129, this would not be true. So the else would be like this. So when duty cycle is 129, half of the time the output is on, half of the time output is off. This is actually where the LED is connected, pin D6. In the pictures we had, yeah, PD6 is LED is connected here. We can have that also, not a problem. Let's see what else is important here to know. Yeah, this is the code. I hope it's clear for everybody how this changes. And this microsecond is because we want like multiply this. Let's say this is 78 microsecond. Why 78 times 255? What number you will get? If you get 78, okay, I will pause and calculate a little. Okay, I multiplied this number with this 78 times 256, so you get 968. It's about 20 milliseconds. This is microsecond, then let's say 20 microsecond it becomes. So here 20 milliseconds. Every 20 milliseconds this loop finishes and goes and this is basically deciding that our pulse width is 20 milliseconds, and yeah, just that this is deciding your pulse width, entire pulse width, which if we say we want it to be like the frequency that we will get, if it is 20 millisecond, if you divide the 1000 to 20, you will get frequency of 50. So let me write it here also again, and then you will have it in the video. Yeah, this is now I just wrote here. This is the formula. It's approximate value. So we want to have a frequency of the pulse that we send to the motor to be 50 in every second. 50 times we cut it, send pulses. Or pulses are like 10 millisecond high, 10 millisecond, for example, 10 millisecond high, 10 millisecond low. And in 1000 milliseconds, we will have 50 hertz, 50 times the pulse. So this is if you want to just make the make pulse width modulation with push buttons, two push buttons to control and the delay function. This is basically only loop and the delay function. The other option is to use the timer 0. Yeah, timer 0. This one, if you are using, we can set the in the class you saw that we had this. Let me get that also. Okay, you remember this, that in the class we talked about. This is, for example, timer 0, that it counts from 0 to 255. Now we can use the overflow interrupt when we are using the timer 0 for controlling the pulse width module. pulse width modulation task. So this is the code. This is entire code that we need inside the main loop. Let's see, what is this? OCR 0, output compare register 0. It's for the timer. This is basically the register that timer count will compare itself with, and when it reaches here, it will do something. For example, it will set on some output, or set whatever we do, it will do something when the timer count becomes equal to this OCR. In here, we are when the push button is pressed, we are changing this, and we are adjusting it up and down. In this one was the duty cycle. Here it is the value that is saved in this register OCR 0. We add to it, or we deduct value from it or add to it. So with the push buttons, we are controlling this. And why is this 65 and why there's a delay of 20 milliseconds here? Let's check them. Let's go to the interrupt, timer 0 overflow interrupt, and we have timer 0 output compare interrupt. Two interrupts are active, so that in one of them we reset the timer. In the second, in one of them we turn on the the output. We set the output, and in the other one we reset the output. Output is the signal that is going to the transistor for controlling the motor. So in one of the interrupts, we set the output, and in the other one, reset. Set means put it as 1, and the output. Reset means put it as 0. So this is the main code. You can see we are using just to manipulate the OCR1, and the OCR1 we are letting it to be between hex value 65 and 60 and FF, basically 255, and you can calculate what is 65 in decimal. Okay, I think it's some, I cannot say, maybe it is 50, maybe it's 90, maybe about 90, let's say. So let's go up, and we see two interrupts that are related to the timer 0. This one, that is, you see, this is the, here is this orange one, is the configuration for timer 0. The clock value, we should put 7.18 Hertz. Using the prescaler, we get this value. The timer should work in the normal mode, and the timer period is the same, 19.96 milliseconds, is because we want to have the 50 Hertz. In every 20 milliseconds, this timer should turn one round, from 0 to 255 should count. So, and these are the how you get to these values. Check cells. This is how you configure the prescale for this timer to reach to this time. This is timer counter register that will. This is the number that is counting. Here in the beginning we put it and we set it as 64, and then we go up. Here are the two interrupts. In the middle was the configuration. Here is the two interrupts. One interrupt is overflow interrupt, and the other interrupt is output compare interrupt. Overflow means when the timer counts and reaches to 255. Output compare interrupt means when the timer count value is becoming equal with the value that this OCR 0 that we had. We are adjusting that, and here we say when the timer count value, this is the timer count value, this register holds the timer count value. When this number becomes equal with the OCR value, this interrupt happens. So let's see what we do in the overflow interrupt. This is just, you need to a little concentrate. Overflow interrupt, in the picture, I would say overflow interrupt is that when the count value TCNT0 is this one that is increasing, the number that is saved in it, TCNT comes and reaches to 255. Here, this code is what we will do here. Let's see what we do. First thing we do is that we do TCNT0 equals 64. We give a value to the counter register here so that it doesn't go to the 0 to start and to count. We tell it to count from this. Let's say in here, instead of 5A is 64. And we say when it's reached here, we give the TCNT a value of 64. So it becomes here right away and then starts counting up again. So we are, with this timer 0, we are deciding that we are going to be having this like a value, this green wave. And the time gap for it is 91. This 21 is for that. But for if you put 60, what was the 60 something? If you put 64, the timer will get some time about 19.5 millisecond or something. So it's a bit less than this. You see, 5A, 6.3 will go a little higher. So this gap will be a little smaller, about 19. So in here, so the with this interrupt 0, we determine that every time the timer counter comes to this number, and from here counts to 255. It to 0 FF. It's hex values. So with this line, we limit the timer to be here in the green like wave. And then here we set output to 1 also. So when we are reaching to here, we give to the TCNT0 a value that comes here. And at this time, we set the output also. We turn it on. I hope that's clear. Then this one is okay. We give a TCNT value when we have reached to the 255. We reset the timer counter's value to be 64 and set the output. So the motor gets the power. The pulse goes to the high value. And what happens to this compare value? When OCR 0, this one, OCR 0 is the value that we want the counter that is counting here compare itself to, and when it reaches there, it should be something. We cannot give OCR 0 anything less than this wave's range. If we give here, the timer TCNT will never be equal with it. So we have to give it something between 64. It was 64. Yeah, 64, hex 64. Between 64 and FF. So we should have the OCR 0 limited between over 64 and under f0xff. Okay, I hope everything is clear. This is like, so with the overflow interrupt, we limited the timer to move over the green wave, for example. And with the OCR 0, we will decide when to turn off the output. We set the output in the overflow interrupt. Then we have to somewhere turn it off also. So we can put OCR value here depending on the push buttons when we increase or decrease the OCR 0 value. This is the compare value. We can give it some number between 64 and FF, and depending on where it is here, the motor will be on and off. Like, so here the motor will be on. As it increases, when it reaches to the OCR 0 value, it will turn on the turn off the motor, not on. Yeah, here turns on, somewhere here turns off. If you put OCR 0 equals 255, the motor will be on all the time. And if you put OCR 0 equals to 65, for example, it will be basically always off. The motor turns on and right away turns off here because it becomes OCR 0 value. Yeah, here we set the motor, here we reset, and in the main code we manipulate the compare value that we had. I hope everything clear. Later we will see how we set this timer 1 also. And next is that using pulse width modulation using timer 1. Timer 1 is a bit more complicated because timer 1 is a 16-bit timer, and 16-bit means that compare value OCR1 has two bytes. One byte is the low byte and the other is this high byte. Entire these codes that are here, you can see this is way longer than that. Entire this code is because we have to control when we are it's like we are adding 1 to the 9, and when we want to add to the 9 we have to write it becomes 10. We have to check if on the left side of the 9 the value of this, or there's any like digit or not. If it's not, it's 0, but if it is 1 there, then the next number will be 20. If it's 0, it will be 10. In decimal, it's like that. In the hexa, it's like that. If you have like FF, the next number, like if you are adding FF plus 1, this 1 will cause FF to be 0, and this 1 will be added to high byte. This is why we are like here we are writing the entire code. And I have to explain, but it is like okay, I will try to explain. For timer 1, let's say we have to configure it also first. For initialization of timer, it happens that we use the clock values in order to get the optimum value for this. We want it to become when we are using this timer, we are using 100% timer for the calculation. We don't for pulse width modulation, timer is doing all of it on its own, and we just in the main code we just do the manipulation of this compare value, which has 2 bits. If 2 bytes, if it was only 1 byte, it would be exactly like this, that OCR where was this? Here, OCR plus plus or OCR minus minus when push button is pressed. But here, when we are pressing the push button, we have to check OCR. If it is 0, then we have to check if the high byte is bigger than 0 or not. If these conditions are okay, then we take 1 from the OCR 0. OCR1, A is because it has two outputs, A and B. A means that it's the A output. The high H means that this is the high byte. So we take 1 from here off and make the rest of it 255. It is like 10 minus 1. You want to make 10 minus 1. You make the second number, which is 1, 0. And instead of 0, you write the 9. 9 is the maximum number that is 1 digit can have. And 1 byte can have maximum 255. So we write this here. And if so any of these ones that are not okay, this is here, this one is for this F, there's this else. If the OCR was 0, if it was not 0, low was not 0, just deduct 1 from it. And if pin B, if the other pin is pressed, if OCR low is equal, here we have to increase the value when the push button is pressed. We check it. If it is 255, and if the OCR1 high byte is 0, then we add to the high byte 1 and to the make the low byte to be 0. Else we just add to those low byte. This is like, this says, let's say the example of adding a number to 9. Here says, I want to increase this value, decimal value, that is 9. Here's 255 is the maximum value in 1 byte. But in 1 digit, I have the maximum of the 9 in decimal. So I want to add 1 to the decimal value. I have to check if this one is equal to 9. Like this number, like x, the number is the x, for example. If the x is equal to 9, then check the left side of it. If the number in the left side, which is the high value, like is 0, so it means I have 9, not 19 or not 29. The left side number, which is higher value, is 0. Then increase the high value. So in the left side, which was 0, I put 0 plus 1. It becomes 1. And the 9 itself becomes 0. This is the 9 itself. So the value that I will get, 9 plus 1 will be 10. Okay. And if this was not true, if this was not 9, if this 1 digit was not the maximum number, for example, it was 7, just add 1 to it, becomes 8. 7 plus 8, 7 plus 1 becomes 8. So this is the mechanism for controlling the higher byte and adding the number to it. And the delay millisecond here is just, what is it doing? Let me think about it. So the delay here is basically controlling how fast the number should increase or decrease. Because when you are holding your the push button, it can instantly increase this number to 255. But If there's a delay here, with adjusting the delay, you can decide how fast you want to reach to the highest speed or decrease the speed. Like you want to the motor to be like reaching from the lowest speed to the highest speed by pressing the push buttons. Here you can just put a delay, and this delay determines that how many times this how long this will take for example this compare value to reach from 0 to 255. That is for that. Let's go to see how the timer 1 is set. Yeah, the clock value is selected by the prescaler. This is the type of the pulse width modulation that we have used. Top like 0 and 0, 1 FF. It means the timer will count from, it's not anymore 255. This one can count like way higher than 255. So here we tell it just it should count. This is basically another 255. So it will be about 500 something. Yeah, 511 about. This number together will be like 511. I'm not sure, but it's about. So the top value, the timer will count from 0 to this value, and then here we tell non-inverted. The output should be inverted or not. When we set it, the output this is doesn't make difference. You can switch it. It determines when a timer is not activated. The output should be like, for example, 1 or 0, and by activation of timer it should toggle. That's the only thing. Input capture on falling edge. Here it's set that the capture of the the timer will capture the signal that is falling down. It will read that. If it's going up, it will not. Rising edge will be ignored by the timer. The timer period is 16.38. If you divide 1000 to 16.38, you will see some number about 60 hertz. That's why we have calculated the timer period to be 16. And if we put OCR1A period to be 16 millisecond, width to be 14 point. Let me, here I have to check again because there's too much details. I need to be sure everything. Okay, let's continue. This number, I'm not sure why I have written it, because we have the timer period is 16.38, and this is what it is. It means the timer will make a round count from min to max in 16.38. So let's go. I will show how to create this quad. Oh, wait. Timer period is, this is timer 0. Yeah, timer 1 is okay. Timer 1 is creating the pulse width modulation totally on its own with this period. And yeah, OCR1AH in the beginning, it's determined to be this one. High value is 1 and the low value is CC, and this means 460, and the maximum value becomes 511. Yeah. So if you put this value here, CC and 1, the high value is 1, and CC, this is basically you are giving this number to the 2-byte register, and the decimal value will be 460. and 460. The timer basically will count from 0 to 460, and then when the timer becomes 0, sets the power, sets the output. When the timer timer count reaches to this value 460, turns off the output, and after that it continues counting to the 511, and between this range 460 to 511 the output is off. And this is why there's 14.74 millisecond here. It means the pulse width that is high, it's 14.70 like 14.749 milliseconds. It's high, and about let's say 2 milliseconds is low. So the pulse width is about like 85%, 90%, 90 over 90% if we use this setting. But OCR1 AH and L, we will manipulate it in here with the push buttons so that we can get different pulse with like duty cycles. Let's go to the software so that we can. Oh, it is complicated. So, new project. Again, ask the same question like always. Yes. I will. The first one that was just with the delay function. We don't need to do any configuration. Basically, I can just set the ports to be output and pull up the push buttons, and then it will be done. But for the second method, which is with the timer, I have to add like set the timer 1, and for timer 0, and for the automatic 100% using timer for making pulse width modulation, I should make the timer 1 setup. So right now, let's say we want to set up the chip for only delay function. Only thing I have to set is the push buttons. Port B, input 1 and input 0 and 1, they should be pulled up. Where was the other two connected? Let me check. Here, LED and the transistor connected to PD6 and PD5. So let's make them output. PD6 and PD5 should be output. 6 output, 5 output. And basically, this is all you need to use only the delay function. I could make it, but it's like everything would be 0, timers disabled, like there's no interrupt enabled, anything. And it's like any usual code that you have made it before. But now I want to show how I will set up the timer 0 for it. So this one is done. Ports bit 5 of the port D and bit 6 of the port D are output. Bit 0 and 1 from the port B are pulled up, input pull up. That's for the push buttons. Now let's go to the timers. This is very precise. You need to pay attention what's going on. Before everything, you should have the chip to be set up to the correct frequency that you want it to work with. Because after setting the timers, you cannot change this. It will mess up the timings. But this is, we know that we want to use it with the hash megahertz, 8 megahertz. So we come here, timer 0 is this one, it's a 8-bit timer. In this one, we wanted to have overflow interrupt and compare match interrupt. This two number was needed. And then you wanna have, this is stopped right now. You want it to work with, what was the frequency we wanted? We wanna have 20 milliseconds period for the timer. 20 milliseconds. Let's see if we have this, for example. This becomes 2 milliseconds. It's too fast. Let's go lower, 8 milliseconds. I think it was 7.8. Yeah, here we get a 32 millisecond. And with this, let me check in there what number was given. 64. For timer 0 configuration, in the beginning it was, timer 0 configuration is 64. TCNT0 is 64. So we wanted to start from here. And so here we give the timer value 64. This is in hex, it's not a decimal. And the compare value, we don't have to give right now because we will manipulate it. But here, let's see. I'm giving it like 6. So later you will see where it will go. This is basically OCR1. The number that I'm putting here, it will go to the OCR0, the compare value. So I activated this one, overflow interrupt, and I activated the compare match interrupt so that I can use, when I put the 64, you can see here, this number, it's about 19.9, 20 millisecond, which will give me 50 hertz frequency. That is all normal mode we are using. We could use different other modes, but normal mode is suitable for us right now. The output is disconnected. We could use that the PWM pins could be connected to some output, but we don't want it. We just want to set the port that we want. So let's see. If we had for timer 0, let me show which output is. Timer 0 is connected to, this is the OC0 output, compare 0. This is for 0. So if we wanted to use the connection of the timer 0, we had to connect our output to here. But we don't want, we want to use this PD5 and 4. So we disconnect this PWM connection. We don't want to use it. Okay. So not connected, disconnected. Normal mode frequency is this. 64 is here, the timer count value. We tell that timer goes to the maximum, then should come to the 64 and start to count up again. It should not go to the 0. And then let's see, like if I change the frequency, for example, here, this will change, the time here will change. So this one, and you see it's 19 millisecond now. If I go to the chip and change my time here to the 1 megahertz, let's see the timer 0, how much become. The time become like 159 millisecond. This is a second, so 159 millisecond. It's almost 8 times more. Yeah, 20 multiplied by, it was 19, multiplied by 6. Yeah, the time period is not exactly 8 times slower. It is like 6 time. 2 times 8. Oh, 8 times, yeah. It is almost 16 milliseconds, 160 millisecond. 160 is 8 times more than the 20. Yeah, so, but I'm going to fix it. I don't want that. Let's make it 8. Yeah, 8 times slower it becomes. Timer 0 is, this was the timer 0 setting. This 19 comes from here. If we wanted to use only timer 0 for the creation of the pulse width modulation, this would be it. I should go here and do program save. But I want to show how the timer 1 also works. Timer 1 is also important. It is a 2-byte like timer, 16-bit timer. So let's see how we set the period of the timer in this one. In this one, let's select system clock is the source. Let's see what options are like T1 pin falling. T1 and T2 are T1 falling edge and rising edge. This is if you want to have external clock as a source of the timer, you can connect to this T1 and T2, but this one could have a T2, I think TCP1, but we just wanna have it system clock as a source. And the frequency, as I remember, it was 31. Then we get this. If we say the top here, the top is 0FF, this normal one. It counts until the 0FFF. We want to use the pulse width modulation with 1F top. So if I use this, now you see timer period is 32. Let's see if we can change it. 32 was not what we wanted. So we have to give compare values here. Output compare A, we wanna, if we wanna use this, we have to connect to the output compare non-inverted PWM. You remember the A. A is, again, I checked the drawing. The A is this one, so it will be controlling the LED. LED is connected to this pin. It doesn't matter, we can switch this wires here later also to control the motor or LED. But now this will be connected to the LED and control that. So this pin will, 5 and 6. No, this is the motor. It is not D5 or C1A. So A is correct. We have to, it's for the motor. Non-inverted. B is disconnected. We don't use that. But right now the time is 32. The compare value, compare A was, I remember, was the low byte and the high byte was 01. High byte 01, low byte was, we should be, value should be CC. And the compare value, which one was the compare value? Was this. High value was 01FF. Let's see what we get with this configuration. Nothing. Capture. Let me double check this. Okay, I see we have to select here. You can see what happened. Something is here. Let's see. Wait for the program is not responding now. Is it the code vision? Close the program. Let me see which program is going to close. Yeah, code vision close. But I'm not gonna close the video. I will just open this again and just show the last part, how you configure the timer one. So it's just few minutes to do that. I'm doing this again. Comes here. The chip should be 32. The ports would be not this one. It should be port B. Pull up. Port D 5 and 6 output. Timers. Timer 0 was supposed to be with this. And the value would be 64. And mode is okay, output is connected, overflow and these are false. On timer 1 should be the here we had the 01 cc basically, and the timer output is wait, this is the normal, so we have to select this fast PWM 1FF, top 1FF. So we will get, if we, after that, if we connect this to non-inverted, the system clock should be this one. So we had 16.384 millisecond, and with the setup, the OCR1A, this one, output compare that we put here, as you can see, it's a 16-bit register, so we have to put this. Then we will get pulse width of 14.7 some like milliseconds. Now we go to the generate, save and exit. And now let's go to the desktop again. In here, the project descriptions, new folder, DC motor. DC motor. Again. And save. And this is how it's made. The same file is made. Right now the libraries are not added. The interrupt is added exactly as it was. First it sets it. Here we should add like set and turn on the output. This is for the timer 0. Timer 0 output compare output, that with the OCR1 we will control the pulse width. The timer 1, which is the important one, yeah, those numbers that we put there, they came here for the output compare value. For the register, the A output is, the high is 1, the low is CC, and all the rest are like we had in the code. This is here. Pulse width we will get like that if we have the output compare value, and everything. The falling edge, we didn't choose it. If we wanted, we could make it a rising edge, but it's we didn't do anything, so this is the default of that. and overflow interrupt, those are all off. And this is how, for controlling the pulse width, you need to just adjust this, and the output for this one, OCR1A, is this output, PD5 OCR1A. So our motor should be connected to here, the transistor. And that's all. That's how we are creating pulse width modulation using the interrupt, like timer 1, timer 2, or just a delay function. And there is this psi. This command is for activating the interrupt globally. So this also you should know. Okay, I guess this is done. Sorry for the delays. It's just the timers. If you are like not working with them, you just forget where the settings were, and I had to like double check so that I'm not putting any wrong information here. And there will be one more project, and after that everybody will make their own projects. Okay, bye.